So we're going to start with this circuit right here. Last time we discussed BH curve, right? Also including the hysteresis loop. And typically this hysteresis loop, these are given by the manufacturers of a core, magnetic core. So if you buy a magnetic core, or if you go to any manufacturers of magnetic cores, they would mention that this is the materials that they use, or these are the different types of the core materials that they use for their inductors or transformers. And typically they would have a link that points to a PDF, which basically the data sheet of this core. And one of the information that you get from this data sheet is this pH loop, right? So that's convenient. But what if you would like to test the core yourself, right? Yes, they provide the information, but if you want to make sure that, or if you, let's say you are using the core slightly different or under different operating condition than the data that they present in the data sheet, then that's a case where you should test the core yourself, right? If let's say that the test that they use for these curve that they provide in the data sheet is based on a specific waveform, let's say a sine wave excitation, then and then if let's say that you are using it under a different type of waveforms, then I think that's a good case where you might want to test the core yourself and see if it see how the BH curve or the hysteresis loop differs from the provided information from the data sheet. Okay, so that's one case. Another case would be you're going to need this type of circuit to test the core, to test the magnetic core. When, for example, you find a magnetic core, in a lab somewhere, right? Looks good, right? It's an E core or PQ core, whatever it is, ET core, and then you would like to test that core, right? Because you don't have the data sheet, right? There's no way for you to tell, what kind of material this core is coming from. So in that case, then definitely you could do this method where you build this circuit that we'll discuss soon here, and then test the core yourself, right? So those are two different, practical cases where you might need to build your own test circuit to characterize the core, right? Characterize meaning get the BH or hysteresis loop of the core. Okay. In the lab, we'll actually have this experiment, right? The circuit itself is already built for you. So we have a module that does this function of obtaining BH curve. All you need to do, if it's an in-person lab, you will use that module. You are given an inductor and you're given this module, and then you do the test yourself. You perform the test in the lab yourself, right? Now, so those are again the practical aspects of knowing this circuit. Okay, I just presented to you two different practical cases where you would need such a circuit. All right, now the challenge, right? What we are trying to test is a magnetic core, right? So magnetic core means it has magnetic properties, right? Not electrical properties, but magnetic properties. Namely, we learned about this last time and last week, right? Mainly flux, right, or flux density, and then field intensity, right? So imagine that, right? You want to measure flux, and then you want to measure how this core operates in terms of flux, and then in terms of field intensity, right? Per given field intensity, how much flux does this core produce, right? And if you think about it, flux density or flux, and then field intensity. Think about the equipment that you would need to measure this, right? Imagine you go into the lab, right? Standard EE labs, right? And then you want to measure flux density, you want to measure field intensity. What do you do, right? What do you do? which equipment do you use, right? So we don't have those equipment, right? We don't have equipment that would directly measure measure flux and field intensity, right? But luckily, flux density and as well as field intensity, they are related to electrical properties. Right? That's the good news, right? Flux density B is proportional to the voltage applied to this component, this magnetic component, whereas field intensity is related to current, right? So that's what I have right here, is that we know from the previous materials that what is it again? Flux density is proportional to voltage, whereas field intensity is proportional to current, right? So that's what we're going to do. We're going to measure B and H indirectly using voltage and current, which I think is cool, right? You're going to get basically a scale down or up, loop, right? Using voltage and current, right? So that's so I just explained to you the challenges, but then we should be able to overcome these challenges by using circuits that would measure, voltage and current, right? So that's what we do here. We can have a scope, right? And a scope only measures, at least the standard one, right? Standard scope only measure voltage. And so we're gonna have to translate current into voltage. Remember, B is proportional to voltage, so that's no problem, right? But then H is proportional to current. So we should be able to measure current and then somehow transform that data into the scope. And again, scope is typically measuring voltage, so I'm going to convert that current into voltage. But that should not be a problem, right? We can use Ohm's law, right, to convert current to voltage. Okay, so that's what you see here in this circuit. This is the basic configuration of that circuit. In the lab, you'll see the more practical, or more realistic circuit to do this. But in its basic form, you need to have a way to measure the current, right? So this is using two windings. It doesn't have to be, but it's using two windings just to simplify the explanation for this. So you have two windings on this core. This is what you're trying to characterize, this core right here. The first winding, the primary side, you inject current, right? And then that current is being measured. Remember, we will need to measure current, right? That current is being measured, right, through this resistance, which gives us voltage drop across RH, right? And that voltage drop across RH is the same as the voltage that is going to be measured by the scope, right? I'm assuming this is the ground, of course. Okay, so now we have Vx basically, right? That voltage right here is called Vx, and Vx is going to be proportional to current through this inductor, which in turns will give us the indication, give us the behavior of H for that core, right? Because again, I is related to H, and then on the secondary side, right, you have this voltage induced, right? And that voltage induced can now be measured, right, through this low pass filter, right? And then you can see that we are measuring voltage across or the output of this low pass filter, which also serves as an integrator, right? So then you have Vy, right? That corresponds to voltage across the inductor, right? And we need that because voltage is proportional to to flux density, right? So now we can see, hopefully, that Vx is a way for us to measure H of the magnetic core, whereas Vy is a way for us to measure B of the core, right? And B is related to flux, right? B is related to flux. Okay, so that's what I have right here in terms of the equation of the circuit. I have H, which is equal to Ni over Lm, right? So N is the number of turns on the primary side, And then Lm, that would depend on the geometry of the structure of the core, right? That's the mean path length of the core. And then I, that's what you are measuring through this resistor, right? And translating into voltage. So you know that I must be equal to Vx over RH. Okay. And then from there, I know that M is going to be constant value. Lm is also a constant value. And resistor that you use here, right there, is also a constant value. So basically, I'm just going to simplify this into a constant value, K of X, right? Multiply by the voltage that we measure, because you're going to adjust the current, basically, right? And then you get different voltages. And by the way, when you plotting these Vx and Vy, make sure that you do XY plot, right? XY plot setting. And you could do that in oscilloscope, right? You can set the display to do an XY plot, right? So therefore, you are plotting what is it? Vx, sorry, in this case Vy versus Vx. Okay, so that's the H part, which is related to I. Any question on this? And oh, sorry, here's the final relationship between the two, right? That's how I know that voltage that we measure will be a scale up or a scale down version of H. Okay, how about voltage? Now we are measuring voltage across the secondary side. It is proportional to voltage across the inductor, which in turn is proportional to core's field density or flux density. Right? And you can see from the circuit right here that by voltage divider, right, voltage division, you know that the output or Vy must equal to the reactance of this capacitance divided by the total impedance, right, times the actual output voltage Vs or V secondary. So that's what I have right there. That's voltage divider, right? And then we have the equation of Vy with respect to V secondary side with some transfer function right there, right? And then in terms of, I'm only interested in the magnitude of this. So how do you find the magnitude of the voltage right there? Well, that's just a complex number, right? So magnitude of complex number is equal to the real part square plus, or square root of real part square plus the imaginary part square, right? So that's what I have right there in terms of the magnitude of the voltage Vy that goes into the scope. That is the equation right there. Okay. Any questions so far? Okay, and then induced voltage from flux equation, assuming no initial flux. Induced voltage E induced is equal to, which is the same as Vy, that's equal to N d flux dt. And so therefore, oh, this is the typo, so please fix this. Let's see, N d flux dt, so therefore d flux dt. So this would be 1 over N, I believe, right? It should be 1 over N. So please fix that one, sorry about that. Okay. So d flux should be 1 over N dy dt. Okay. So now I can take integral of both sides, right? And if I do that, then I have this equation right here, right? And then when you carry out the integral, you get flux equals to times Vy over N. Okay, and we know that flux by itself is equal to B times A. Remember, B is flux density, right? So if you want to get flux, you need to multiply flux density by the area of the core, right? So B times A is equal to the right-hand side of the equation, and now from there I get the equation for B, which is T times Vy over Na, right? And then I know what Vy is from the magnitude right here. So from here, right there. So I just plug in that equation into here. Okay. Oops. So now I have the complete equation for B, which is equal to T over N times A 1 over square root of 1 plus omega RBC squared, right? Now, n is the number of turns on the secondary side. A is the cross-sectional area of the core. So these two are constants. And then square root of 1 plus omega RBC, right? So this is a certain frequency. We measure this at a certain frequency. So therefore, 2 pi f is fixed, and T is our period, is also fixed, right? And then RB is also the resistor that is fixed, and C is also fixed, right? So we have a lot of constants, right? T, N, A, omega, RB, and C. These are all just constants. I'm just gonna lump them up into one single constant called Ky right there, right? So now I have the second equation that relates B with voltage. That's nice, right? Because what is so nice about this equation? Because I could relate magnetic property B with electrical property that we all speak, right? Electrical engineering, we speak of voltage and current. So it's nice to be able to relate magnetic property into electrical property. Cool, isn't it? So that's what this circuit does, okay? Any questions? So keep in mind that this is a circuit that you could implement in the future if you ever need to characterize a magnetic core yourself, right? And then plus the experiment that we'll be doing, I can't recall, is it the second or third experiment? That's another circuit that you can learn from this class in order to characterize a magnetic core. Any questions?
The B in the integrator circuit, right? The filter. Does that B stand for anything specific, or is it just a?
Which one? Sorry.
And the resist and the like low pass filter, right? The integrator circuit that's past the secondary voltage.
Yes.
Does that B stand for anything?
Oh, that just stands for a resistor that would measure B, the field, the flux density.
Gotcha. Okay. Gotcha. Okay.
Is that what you're asking? That subscript?
Mm-hmm. Yeah, that's what I was asking. If it had a name to it, but okay, that makes sense to that it measures B.
Yeah, because you can see I use H right there. So that resistor is being used to measure H, and that resistor is being used to measure B.
Gotcha. Thank you.
Okay. Any other questions? Okay, if not, let's move on to the next topic. Core loss. Oh, yeah, it's a big topic, core loss. Okay, so introducing solids into a magnetic field causes 3 different behaviors. The first one is diamagnetic. I don't know if I pronounce this correctly. Diamagnetic materials, which would be repelled by external magnetic fields, such as these materials are examples of these materials are water, copper, silver, and gold. So these are repelled by external magnetic field. And then we have the second behavior, paramagnetic materials, which would become magnetized in a magnetic field, but then their magnetism disappears when the field is removed. For example, aluminum, platinum, and magnesium and lithium. Right, so that's the second behavior. So you have diamagnetic, which repels, and then paramagnetic, which becomes a magnet, but then the magnet disappears as soon as we take away the field, magnetic field. And then we have these ferromagnetic materials, referred to as magnetic materials. They retain their magnetic properties when the magnetic field is removed. So this would be the ideal type of behavior of materials that we can use for magnetic core, right? Why? Well, because they retain magnetic properties even after we take away the magnetic field. Okay, so related to this class, we're more interested in ferromagnetic materials, and this part right here, this is just the explanation on the atomic level on how ferromagnetic materials retain their magnetic field inside the core. So I won't go through this. I'll let you read through this yourself, which in turn explains, for example, why it behaves like, or it follows this hysteresis curve, right? And for us, I mean, at least to me, I'm more interested in how to use this curve, right? So if you're interested in the physics behind this, go ahead and read this section, okay? And we talked about last time, right? We talked about that point, which is the remnant flux, right? That requires coercive force to reset it to zero, right? When we first excite the core, it will travel through this first initial BH curve. And then when we apply negative current, or not negative current, sorry, negative voltage, meaning discharging the component, then even if the field is no longer there, you see that, right? When H is equal to zero, we still have some flux remaining in the core, right? And it takes more energy to reset the core into, zero flux, as you can see there, right? It takes negative current to reset the core into zero flux. So that part we talked about last time. That's more practical side of this hysteresis curve, which I'm interested more. Okay. The hysteresis curve profile depends on the material used. For example, soft magnetic materials will have field intensity of less than 1,000, mainly used for inductive components such as nickel iron alloys and silicon iron, sorry. And then we also have hard magnetic materials where we have larger magnetic field intensity requirement, right? And mainly used for permanent magnets and electromagnets. I don't know how to pronounce this, alnico, which is a alloy, right? And then other ones right here. So those are two different, what do you call it, shape of the hysteresis curve, right? Depending on the material. So here are the examples of the two different materials. You have soft magnetic, which requires small amount of field intensity, right? And then the other one is hard magnetics, hard materials. Right? So you can see the big hysteresis versus the skinny one, right? Okay. All right. So then another important thing for us to be aware of is that the area enclosed by the hysteresis curve corresponds to the hysteresis core loss per cycle, right? So that is part of the core loss, right? So magnetic core will have losses as well, just like a wire, just like electrical wire, right? Magnetic core will have losses, and the two different types of losses are hysteresis loss and eddy current loss, which I mentioned right here. Right, so those are the two different sources of core loss. Okay, hysteresis and eddy current losses. And then for hysteresis loss, if you measure it, if you vary the frequency applied to this core, then you'll find out that the larger the frequency, the higher the frequency, the bigger the area enclosed by this hysteresis loss. So the hysteresis loop becomes bigger and bigger and bigger. I think you've seen it before, right? Last time in one of the pages. As you increase frequency, then you would increase the area enclosed by the hysteresis curve, and therefore that would increase the loss from hysteresis loss. Right? And if you plot if you measure, for example, the power loss with respect to the frequency, right, as well as the flux density, right? So not just a function of frequency, but also a function of flux density, right? And then if we plot it on a log scale, then we have this equation called Steinmetz equation that goes like this, right? Some constant, so power loss is equal to constant K1 times F to the power of P times B to the power of Q, right? And P right here, right, in magnetics is not really watts. It's typically given by watts per unit volume. So that's another thing that's unique about magnetic component, is that power loss is not typically given in watts, but rather is given in watts per unit volume. So you have to multiply the volume of the core to be able to give you watts. And B right there is the peak value of the flux density. So that's the peak density, peak flux density. And then F is the applied sinusoidal frequency. Okay.
Professor?
Yeah, go ahead.
What's the second P in the exponent?
Yeah, that's just for different materials, you get a different exponential value, different depending on the components, depending on the materials, right? You have different values. So for example, this is done for what we call 26 material, right? And that's going to be different if you use different materials. You're going to have different coefficients, you know, P and Q. So that's what they are. All right there. So typical P is between 1.2 to 1.8, while Q ranges from 2.1 to 3.4, again, depending on the materials used for the core. Does that answer your question?
Yes, thank you.
Yeah. So again, this is an example where we have this particular material, okay? And then just that one type of material, and then for this graph or for these plots, they measure different frequencies for that same material and different flux density. Right? As you can see from here, the x-axis is the flux density B, and the y-axis is the core loss, and then we have, you know, family of curves at different frequencies. So if you plot the data in log scale, you can see these are straight lines, which is nice, right? Because then we could get the equations easily when you have straight lines. All right, and notice the unit, right? So this is very common, by the way. Okay, this is very common. If you look at the data sheet and you look at core loss graph, it is very common that you'll get these units, milliwatts per centimeter cube, for example. It's always per unit volume, right? So just do not just assume this is milliwatts. Okay, you have to multiply by the volume of the core to get you watts. All right. Note that hysteresis loss data typically assumes sine wave excitation. So I mentioned this earlier before we started circuits earlier, right? The test circuit, that the data sheet is typically provided based on certain operating conditions, right? The information that you get from the data sheet these are typically performed under very specific operating conditions, such as sine wave excitation, symmetrical waveforms, no DC bias, right? And then peak field density, and then only one temperature, right? So if you want to do it at different operating conditions, then you might, then you will be, I should say, you will be needing to test the wave, test the core yourself, right? Using the circuit that you learned earlier. Okay. Lost data are only approximation, can be off by up to 2 times, depending on what kind of excitation you apply to these magnetic components, right? Ideally, you want to apply sine wave, but that's not always the case, right? If you've taken power electronics before, you know that in power electronics we have all kind of shapes of waveforms. It's not just sine wave, right? All these funky looking waveforms in power electronics. So imagine you are trying to use the data that are based on sine wave, but then you are applying different type of waveforms. Then of course that's going to be, the data is going to be off. But I think it still serve good purpose of approximating the loss, right? Here's an example where you see the differences between 2 different excitation waveforms. Basically, the first one is sine wave, the second one is square wave, right? So you can see the loss. Look at the units again. Now this one is energy, not watts. So that's joules over meter cube. You can see the difference in terms of the loss, right? Between sine wave and square wave. Looks like square wave per given flux density has less loss than sine wave. Okay. So that's something that you can actually do yourself, right? If you end up with a triangular wave or what's the other one? Sawtooth, for example, right? Then you can can build the circuit yourself to test the core and test it yourself and get the same graph, and you'll see how it stands compared to sine wave and square wave as an example. Any questions so far? More on hysteresis loss. Hysteresis loss can be explained in terms of how the core stores and releases energy in one cycle of flux excitation. So why is it that the area enclosed by the hysteresis loop represents loss? And that is explained here in this section. Okay, so figure below demonstrate the process. First of all, the equation for energy stored in the core, we're gonna derive this later, is equal to the volume of the core times the integral of H, field intensity applied to the core times, with respect to the field, I keep saying the field, flux density, right? So that's the equation for energy stored in the core, okay? Which is basically what? The area under the curve, right? The area under H with respect to B in the BH curve. So where is it? I thought I have a picture on this. Hang on a second. I thought I have a picture. Yeah, right here. So I'm gonna skip ahead to this page right here, page number 52. So this picture shows that the energy from that equation, right? Energy stored is the integral of H with respect to B, right? So basically, if you want to find the energy stored from this magnetic field intensity 1 to magnetic field intensity 2, then the energy stored will be the area under the curve with respect to B. So it's kind of a what do you call it? 90-degree angle. We're so used to finding the area under the graph this way, right? But now it's actually under the area that is horizontal instead of vertical, right? So again, that's how we calculate the energy stored, right, in the core. It's by integrating the curve or the graph. This is the BH curve, right, with respect to B, finding the area under the graph with respect to B. Any question on this? So that's the implication of that equation. All right. So then going back to that page, here's our H curve, BH curve or BH loop, right? So let's say that I start from, here's the complete cycle, right? There's the complete cycle right there. And from A to B, that's when we have positive current, right? Increasing slope, basically, right? Increasing current. You agree? From A to B, remember H is proportional to I, right? H is increasing from A to B. So therefore I is increasing from A to B. So that means it is charging from A to B, right? So the portion of the graph that starts from A and ends at B, that is the portion where we have, when we are charging the inductor as an example. You agree with that? Okay, and then from B to C, that's a portion where we discharge, not the whole thing, but we discharge the inductor. So we release the energy back, basically, right? Why? Because the current from B to C is decreasing. Do you agree with that? So if you look at the portion right here, or the segment of the hysteresis loop from B to C, you can see that current decreases from B to C. So therefore, we have decreasing current, meaning that we are releasing energy, right? So we store energy from A to B, and then we release energy from B to C, okay? So here's a picture, right? Remember, area under the curve, right? So when we are charging the inductor, let's just assume this is an inductor. When we are charging the inductor, that's going to go from A to B, right? Current goes from A to B. And how much energy is being stored in that inductor? Remember that equation? The implication is that if this is the curve or portion of the curve, that gives us the charging portion of the inductor. That means the area under that curve, which is the shaded area right there, must represent the energy being stored at that time when we are charging it. Is that clear? First of all, any question on that one? No? Okay. Okay, so then what happens when we are discharging the inductor, right? And as I explained earlier, from B to C, right? So that's the portion of the BH curve from B to C. That's when we have decreasing current, right? Meaning we are discharging the inductor, right? So how much energy is being released, right, from B to C? Well, that's the same thing, right? Area under the curve. So area under the segment of this curve right there, right? That's the segment right there from B to C. So the area under that with respect to B, which is that shaded area right here, that would represent, what is it? Energy that is being released. Okay. So then you can repeat the same procedure for the other half of the operation right there. From here to here is when you're charging the other way around, right? You're charging the opposite way. And then you're releasing it the opposite way. You see that? So now, if I go back to the first half, right? If this area, the shaded area, represent energy being stored, and this smaller area represent energy being released, then how much energy is being lost in the process? Must be the difference between the two. Go ahead and subtract the area, the second area. Let's call this area B with area A. Right. So subtract area B from A. So what do you get if you do A minus B? Then you get, what do you get? Then you get this area right here, right? How do I do this? I'm just going to use maybe orange. So you're going to end up with this area. Do you agree with that? Anybody disagrees with that? Just for the first half. Right. Okay. Again, energy stored minus energy released gives us energy lost, which is basically the area inside the curve for the first half. And if you do the same thing for the other half, right there, yeah. So area D subtracted from area C, for example, then you get what? You get energy lost, which is this area right here. All right. So now I just proved to you, I just explained to you the reason why the area enclosed by the hysteresis loop represents the hysteresis loss, the energy that is being lost in the process of charging and discharging, or storing and releasing energy from this magnetic component. Any questions?
For part C, is that energy being stored or is that released because it's negative current still?
No, this is already being stored on the other direction, right? So you're storing, yeah. So you're storing energy on the other direction with negative current, right? So we are done with the positive current, basically, right? Positive current is done. So now we are charging the inductor with the negative current, right?
Gotcha.
Yeah. Any other questions? No? All right. Okay, hopefully that is clear. The reason why the area inside or enclosed by the hysteresis loop represents hysteresis loss or core loss in this case, one of the core losses. Now I believe we're gonna derive this equation. Okay, energy stored in a magnetic core. If we are to neglect the resistance of the circuit wire, then there would be no energy loss in maintaining magnetic field. That would be nice. However, energy is required to establish the field, and it can be then be recovered when the field is destroyed. For a toroid, the induced voltage E at any instant is equal to, that's the induced voltage, right? N times d flux over dt. right? Where N is the number of turns and phi is the magnetic flux. If the current at any instant is I, then the instantaneous power, right, will be voltage times current on the circuit side, on the electrical side of the inductor, right? Remember, inductor has two sides, okay? Electrical side and magnetic side. That's why it's more challenging, right, to design and to analyze. The energy in joules released from the coil in a time dt is therefore equal to E is equal to P times dt, right? So E times I times the time, basically, right? And E times I, you know what E is from the first equation up there. So just plug it into here, you get N d flux dt. I just leave it as I, and then dt, right? And then from there, you see that the dt cancels, right? So now I have energy released from the coil equals to N times I times d flux, or d phi. Oops, sorry. Okay. So then the total energy stored from zero flux to maximum flux applied to the core becomes just the integral, right? From 0 to the max of Ni with respect to the flux itself, right? So that's how we get the total energy stored from the flux. And so that's the equation for energy stored. Consider a magnetic circuit of length L, right? So magnetic path length L, which is constant depending on the structure, right? And cross-sectional area A, which is also constant per given magnetic core structure. Okay, then, and also we know that flux density is equal to flux over A, and A is constant, okay, per given core. And so therefore flux is equal to B times A, right? And then the flux should be equal to A times dB. Right? So first derivative of flux should equal to first derivative of B. First derivative of flux is equal to first derivative of B times A, and A is constant, right? Okay, so now I have d phi is equal to A dB. All right. From before, the previous equation for energy stored, the equation was E stored, the stored energy is equal to the integral of N times I times d phi, right? And then now I know that d phi, I think that's how you call this, right? Phi, that Greek symbol. D phi is equal to A dB, so I'm just gonna substitute that into here. So now I know that the equation for stored energy in the core is equal to the integral of N times I times A times dB. Okay, so far so good, hopefully. All right, then I'm going to do this. I'm going to divide and multiply by L. I could do that, right, mathematically. So divide and multiply by L. If I do that, then you know what this is, right? Ni over L, that's H, right? That's the equation for magnetic field intensity. And then L times A, what do you call that? Magnetic path length times the cross-sectional area of the core. That's going to be the effective volume, right, of the core. Right? So by this simple mathematical trick, I would say, right, multiply and divide by L, you get a new equation. Right? Okay, you can rewrite the equation for energy stored to be the integral of H times the volume of the core with respect to B. And guess what? That's the equation that I showed you earlier, isn't it? That energy stored is equal to volume times the integral of H times dB. Is that right? If I'm not mistaken. Back in this previous page, one of the previous pages. Where is it? Oh.
It was page 48.
Okay, one more. Yeah, right there. Okay, so that's the proof to you that energy stored in the core is equal to the volume of the core times the integral of H with respect to B. Okay, so I just proved to you that mathematically. Okay, going back to that page. We are not done yet. although this equation was derived for a toroid, it can also be demonstrated. It can also be applied for any other cores. Okay. For BH curve shown below, that I just explained to you. I explained to you this earlier, right? That this equation just means that you find the area under the curve with respect to B. When you have a BH curve like this, right? So that's typically what you get for magnetic core, a BH curve, and the energy stored would be the area under the BH curve with respect to the B, right? Okay. We also know that the magnetic field strength H is related to the magnetic flux density B by the equation B equals to mu naught mu R times H, which gives us H in terms of B, right? Equal to H is equal to B over mu naught mu R, and that should be convenient because the integral is with respect to B, right? It'll be good to be able to express, H, as a function of B, because then we could integrate we could carry on the integral, right? And so that's what I did right here. What happened? Okay, right here. So I rewrite the equation for energy stored in the core. Same thing, volume times the integral of H, but now H, I replace it with B over mu naught mu R with respect to B. So now I could do the integration, right? I could carry out the integration. And if you do that, you get this equation right there for the energy stored in the core, which is equal to 1/2 times the volume times the field, again, I keep saying field, times flux density squared divided by mu naught mu R, okay? So that's the equation, one of the equations to calculate energy stored in the core, okay? And some time ago, I tried to derive this in terms of inductance, right? Because we are building, what we have here is inductors or transformers, right, which have inductance. And so it should be related to 1/2 Li squared, as we learned from physics, right, or from circuits class, that energy stored in the inductor is equal to 1/2 Li squared, right? And these should be related to the core because the inductor is using the core, right? So, again, some time ago, I derived this with inductance. So stored energy in the inductor, as we know, is 1/2 Li squared, right? And then hopefully by deriving it from here, I get the same result right there, right? If I get the same result, then I can prove to you that this is related to the inductance as well, right? So that's the purpose of deriving this. So again, I start with the inductor energy, right? 1/2 Li squared, and then recall from voltage induced across a coil that induced voltage is L di dt for inductor, but L by itself is called self-inductance, right? So self-inductance is equal to N d flux di, right? And so inductance value L for a coil is then L is equal to N d flux di. Okay, that's just the L part, right? And then in general, in terms of change in the flux and change in the current, right, this is where the change are very tiny, right? But in general, L is going to be N times delta flux over delta I. So d phi over delta I, delta phi over delta I. Okay? And we know that the equation for phi is related to B, right? Remember, B is equal to, what is it again? Phi over A. So therefore, phi is equal to B times A. So delta phi should be equal to delta B times A. Remember, A is constant, right? That's the area, cross-sectional area of the core. And then delta I, just leave it like that for now, okay? And then I know that B by itself is related to H, right? Mu times delta H times A, okay? And then we also know that H, delta H, is related to I, right? It's equal to N I over LC. So if it's delta H, that's going to be N delta I over LC, Okay, so now the new equation for L for our inductor, now it's going to be a longer equation, right? Starting from N mu delta HA over delta I, now I'm going to replace delta H right here into that equation. So then I get this new equation right here, right? And then if you look at the equation, you should be able to simplify. You can see delta I cancels, right? And then you have N squared, and then you have mu A over L, right? And then in addition to that, right, now you have a new equation for inductance. Inductance as a function of number of turns, L and AC, right? So that's a inductance as a function of the geometric or the physical structure of the core. I don't know if you noticed that, as well as magnetic property. Keep in mind that this is mu. Mu is equal to mu r times mu naught, right? That's magnetic property. So what I just showed you here is that now I relate what do you call it, electrical quantity, right, inductance, with respect to magnetic core property. Okay, mu naught, mu r, and then cross-sectional area, and then mean path length. Okay. Now I could also simplify that equation into this one right here. It's not simplified yet, but if you rewrite the equation this way, then I know that L over mu A is none other than reluctance, right, of the core. Right, so that's the reluctance of the core. So therefore, inductance, right, turns out to be equal to number of turns squared divided by the reluctance right there. Right. Okay, which is again the longer equation version of the equation is this equation right here. If you don't simplify this portion to be our reluctance, okay, to be the reluctance of the core. But back to the inductance equation, the energy, right? Energy stored in the inductor is equal to 1/2 Li squared, right? And then L now that I derived that L equation, I'm just gonna plug that into here, right there. And what do I get? I get this equation right here. Yes? Please double check the algebra. Okay? I might have a typo, but I think it's correct so far. And then, however, the current I is related to the flux density B. So H is equal to Ni over Lc. So therefore, I is equal to H over N Lc, which is equal to B Lc divided by mu N, right? I'm just replacing H with B over mu, right? So if that is the case, all right, what happens here? Let's see. What did I do here? So what I did is I replace I, looks like, right, with this equation. Right, so go ahead and plug in I into that equation right there. And I get this equation right here. Right? All right, so now once I have these equations, a long equation, and I see that some of the terms cancel, right? One of the LC cancels, and then one of the N cancels, right? So you can see now the equation reduces to this equation right there, right? Which in turn reduces to that equation right there. Now the question is that the same equation that we have earlier? Let's see. Yeah, right there. See, that's the same. Remember, mu naught mu r is equal to mu. 1/2 V squared over mu. Is that the same? Double check. 1/2 V squared over mu. Exactly the same, right? So I just proved to you that by starting with inductance energy, at the end I get the same equation, right? Whereas the previous derivation, I didn't use any inductance energy at all, right? Okay. And in terms of H, I can just change this back into H right there, right? At the end, you get 1/2 LC phi times H. Okay? Just more equations for you to choose from for calculating energy stored in the core. Are there any questions? No? All right. Okay. Flux waveform from applied voltage. Okay, so now flux in the core, phi of t, or is it phi? Yeah, it is phi, right? Due to a coil of n turns is related to the applied voltage across the coil v of t by this equation right there, right? How was it again? Voltage induced is equal to n d flux dt, I believe, right? Let me go back. I have that somewhere. Right here, or yeah. Yeah, right here. So flux induced, not flux induced, voltage induced is equal to n d flux over dt. If you cancel the di, right, you can see that flux, not flux, that voltage induced is equal to n number of turns times the first derivative with respect to time of d flux over dt, right? So if you move the dt to the left-hand side of the equation, right, and then n, then you get this, right? You get d flux equals to, I'm just going to use voltage V now instead of E, right? 1 over n voltage dt, right? So if you take the integral of both sides, then you get flux with respect to time equals 1 over n integral v dt. You agree with that? And that's what I have in that equation right here. That's how you relate flux with voltage applied, right there. Okay. So flux with respect to time, the value of the flux with respect to time is equal to 1 over n integral from 0 to t of v of t with respect to time dt. Okay. So that means if I know the waveform, the shape of the waveform for the voltage, then I should know how to sketch the waveform of the flux that is flowing inside the core, right? Remember, voltage is what we apply across the inductor or transformer, right? And flux is what's flowing inside the core, right? So if I know the shape of the waveform of the voltage applied to the coil, then I should know how to sketch the waveform of the flux flowing inside the core. For example, if you can see that if the voltage equation is a sine wave, then the flux equation should be a minus cosine, right? Minus cosine wave, right? So that's the flux shape right there, okay, with respect to time. If, for example, or there's the picture that shows you, okay, we are applying voltage, and then what we want to relate now is the shape of the flux waveform with respect to voltage. And then the second example, let's say I applied a square wave, right, on this voltage. What kind of shape of the flux that you get inside the core? Well, it's going to be the integral of the square wave, right? What is the integral of a positive flat line? Well, that's going to be a positive slope, right? What is the integral of the negative flat line? That's going to be a negative slope, right? So now you can see that if you apply a square wave across this coil, then the flux that is inside that core will shape like a triangular waveform, okay? And there's another example here, right? You got a, what do you call it? Pulses, right? With some on time. So you can see that again, flux follows the integral of the voltage, okay? Any questions on this? No? All right, now we can move on to eddy current loss. All right, this is the second part, the second type of loss, right? The first type of loss is core loss, right? The worst loss is actually eddy current loss. Hysteresis loss is proportional to F. Eddy current loss is proportional to F squared. So as you are increasing the switching frequency, then eddy current loss becomes, much higher, right, by a factor of F squared. Recall that Faraday's law of electromagnetic induction. We have voltage induced from changing flux, right? So as long as you have changing flux cutting across a what do you call it, a conductor, then you have induced voltage, right? So here's an example visually, right? You can see that we have a rectangular conductor, let's just say, a rectangular conductor, and I'm cutting through right there flux with respect to time, right? So imagine flux is flowing into this rectangular conductor with respect to time, right? So then you have, if the conductor has an open terminal right here, then you're gonna get voltage induced across this terminal, right? Let's see if I can define. Is it plus minus this way? You can double check. But anyhow, you're gonna get some induced voltage across that terminal, open terminal, right? So then what happens if you short this terminal? What's gonna happen? If it's open, you have induced voltage, and this is a conductor, okay? But then if you short this, what's gonna happen? Then you're gonna have current, right, flowing. You're gonna have current flowing around, right? If you short it, right? If you short this, then you're gonna have current flowing around this core, right? And you can see that's a short current practically, right? There's no resistance except for the resistance of this conductor, right? So it's practically a short current, right? So that's why this is a dangerous current, right? Because even with the, what do you call it? Even with this small, for example, conductor, this conductor can get heat up because of this current, okay? So then what if I add more rectangular conductors inside that big one, such as number 2 right here, number 3 right there, number 4 right there, and the same flux? What are you going to get? Well, you're going to get more currents, right? More currents flowing here, more currents circulating right here, and another current right there, right? So we have several short currents, right? And because of the amount of flux that is being enclosed within each rectangular core, then I know that current I4 must be less than current I3, must be less than I2, must be less than I1. But nevertheless, we have a lot of currents flowing through these conductors, right? So then this is what we call eddy current loss, or eddy current, I should say. This is what we call eddy current, right? And this becomes even worse if, right, if these rectangular conductors are densely packed, touching each other to form a solid metal plate, right? So imagine if I put more and more in between those frames, now it becomes like a solid frame right there, right? And this is basically our core, magnetic core, right? Our magnetic core is made of solid, right? Solid structure like this. So then what's going to happen? Then you have infinite number of currents, right? Circulating around these solid metal plate, right? And that's dangerous, right? That's why eddy current loss is such a dangerous loss, even at 60 hertz, right? If you're not careful, that's gonna heat up the core, okay? So then how do you reduce eddy current loss, right? Just like you would for current, right? So the analogy for this would be this. If you have one wire, right? Let's say I have 10 amps. So yeah, let's use X amps, right? And then let's say that the resistance of this wire is R. And what is the loss here? What is P loss? Call it P loss 1. That's equal to X squared times R. Yes, I squared times R. Okay. So then how do you reduce this loss? Simply by providing multiple paths, right? Additional path for that current. I'm going to use the same wire, right? Now I'm going to split the current into two currents, right? So the same X right here. So that means if this is R and this is R, then what do you have here? X over 2 and X over 2. Yes? So what is the loss here now? Well, what is the loss from 1? That's going to be X squared. So now it's going to be X over 2 squared times R. Yes? What is that equal to? X over 4 times R. Agree? But then there's 2 resistors. So therefore, the total loss for the second case will be equal to 2 times X over 4 X squared. I forgot the square. Let me do this first. There you go. Yeah. So then 2 times X squared over 4 times R. What is that equal to? X squared over 2 times R. Right? Go ahead and compare the two. Which one has less? The second one, of course, right? So simply by allowing multiple paths for that same current, you reduce the loss. In this case, if you add another path, you reduce the loss by a factor of 2, right? You halve the loss. Same thing here. That's the analogy, right? With flux, eddy current loss, the way you decrease the loss is by splitting the flow, not the flow, but the amount of flux that cuts through this metal plate, right? How? By dividing this metal plate into 2, for example, and you have to use insulator in between. So they're not shorted, right? So by splitting, there you go, splitting the flux into 2, just like you split the current into 2, that would decrease the eddy current loss, okay? So that's the same approach that we do for reducing eddy current loss. Divide it into 2 sections, and you get less flux. Flux now being halved instead of full flux. Now you have flux over 2 for one segment, for one portion of the metal plate, and the other half for the other metal plate. So you reduce the loss by doing this, right? But of course, dividing it by 2 is not going to be enough, right? You have to divide it by many segments. That's what we call laminations, right? Rule of thumb, for a given core, the eddy current losses decrease in proportion to the square of the number of laminations. That's the rule of thumb. So that's called laminations, by the way, okay? That different segments is called laminations. So right here. So instead of one solid core, you stack some laminations to make the core. So you can see this person stacking up the core, right? Each one of these, right? That's a lamination, right? When you stack them up, then it becomes a core, just like that. See that? So now you know why, if you look at especially power transformer, the big one, utility type of transformers, if you look at the core, it's not going to be a solid core. It's going to be layers of laminations. Now you know why. Now you know why there are laminations, because we want by doing that, it would significantly reduce eddy current loss. Okay. Any questions on that?
I had one question. So are they insulated between each lamination?
Yep. Yeah, they put some insulation materials. I don't know what exactly, but they have to. Otherwise, you have a magnetic short between the 2 laminations, right?
Yeah, gotcha.
Okay. Any other questions? All right. Okay. Eddy currents impacts the skin effect and proximity effect. You've learned about skin effect, right? What is it? 335, I guess. Skin effect is caused by eddy current induced in a conductor by the current in that conductor, so own current. So if you have a wire and that wire has current, then skin effect is caused by that same current. But if you have 2 wires, right? and each wire has current, for example, then proximity effect is caused by the eddy current loss, eddy current effect from the other wire, right? So if you look at this wire, the first one, let's call it number 1, and let's call this number 2, right? And this will have some flux, right? That causes in the eddy current loss, and the effect of the eddy current loss from that wire number 2 into number 1, that's what's called the proximity effect, right? So one more time, skin effect is caused by eddy current induced in a conductor by its own current, whereas proximity effect is caused by eddy currents induced by the current from an adjacent conductor or neighboring currents, right? That's why it's called proximity effect. So that's the difference between skin effect and proximity effect. Both of them are caused by eddy current, but one is caused by its own current, whereas proximity is caused by an adjacent current. Now, skin effect, as the frequency of a given AC current in a conductor is increased, the power dissipation increases as well, right? This is due to the increase in AC resistance of the conductor caused by the rearrangement of the current distribution within the conductor. So you learned this from 335, I believe, that current concentrates more on the perimeter of the conductor rather than being uniform over the conductor area, right? And that only happens, right? The uniform distribution only happens when you have DC current. But as soon as you introduce higher frequencies, more than 0 hertz, then electrons being pushed toward the surface or perimeter of the conductor, right? And it's getting worse as frequencies increase because the skin effect gets smaller and smaller, right? So imagine the skin effect in DC to DC converters where commonly used frequencies above 300 kilohertz. At this higher frequency, the predicted efficiency should be altered due to increase in loss from skin effect, right? Because now more electrons are being pushed toward the surface of the conductor, thereby increasing AC resistance. Right? The magnitude of this effect, so this is important, the magnitude of this effect at high frequency on conductivity, magnetic permeability, and inductance would require further evaluation of conductor size. So when you select conductor size, skin effect has to be part of the consideration if you operate the circuit at high frequencies. If it's DC, no worries, but if it's higher frequencies, then you need to really consider skin effect, right? And there's the equation for skin effect for low conductivity material right there, right? For high conductivity, it simplifies to that equation right there. Right? I believe you learned this in 335. Penetration or skin depth where amplitude of current density has fallen to 37%, so that's delta. Right? Is that what you call it, delta? Or sigma? I don't know anymore now. Okay, just some constants. All right, and then examples of low conductivity materials are glass, rubber, wood, sulfur, air, Teflon. And examples high conductivity materials are silver, that's the best, copper, 9% less conductive than silver, gold, 24% less conductive than copper, but does not tarnish or corrode, brass, somewhere here, rhodium, 74% less conductive than copper, and so on and so forth. I'm not going to go through all those. Another equation of skin depth for high conductivity material. So we have at least 3 equations now for finding skin effect. This is for high conductivity material. That's going to be 6.61 over square root of F times K. As you can see, is inversely proportional to square root of F, right? So the higher the frequency, the smaller, or the smaller the skin depth, right? Which is not good, right? Okay, let's see. Calculate the skin depth of copper at 20 degrees Celsius with conductivity. This one is sigma, right? Sigma equals to 5.8 times 10 to the 7 at 100 kilohertz. So going into this equation, one of the equations on the previous page, which is this equation right here, for high conductivity material, K is equal to 1. I use MATCAT, by the way, and then mu, and then what is that? Epsilon, and then sigma, and then F, right? Plug into that equation, I get 0.209 millimeters for the skin depth, right? And if you use the last equation, the approximations, right? The last one right here. Oops, sorry, not that one. This one right there. Then the result is not far. It's 0.209 millimeters right there compared to, well, actually they're the same. It's actually the same, 0.209 millimeters. And then the second equation also 0.209 millimeters. So that's good. That's a good approximation. It's actually the same for this one, for this case. All right. The relationship of skin depth to gauge, right? Radius, wire radius with varying frequency shown below, where RAC over RDC is equal to 1. For a given frequency, it is desirable to use a wire with skin depth larger than the radius of the wire, since current will be distributed throughout the cross-sectional area of the wire. What that means is this. If, let's say, this is the cross-sectional area of the wire, right? If the skin depth is that much, then that's not good, right? Because you're only using that portion of the wire, of the cross-sectional area of the wire, right? Which means very high resistance. So it will be good, right, for a given frequency if you size the wire gauge, right, to have, what did I say? To have the radius of the wire larger than the skin depth. Wait, skin depth larger than, the other way around, skin depth larger than the radius, right? So imagine if the skin, this is the radius, right, from here to here. If the skin depth is larger than the radius, let's say this much is the skin depth, right? And then it goes all around the wire, then you are using, right? You are using the entire cross-sectional area of the wire if you apply this rule of thumb as an example, right? Skin depth larger than the radius. Does that make sense? That way you make use of the entire cross-sectional area of of the wire. Does that make sense, hopefully? Okay. I'm almost running out of time, I believe. And yeah, this one shows you log and log scale of how skin depth is, varies with frequency, which makes sense, right? As frequency increases, skin depth decreases, which is not good, right? You're using only a small portion of the cross-sectional area. And over here, it shows frequency with respect to wire gauge. So remember that rule of thumb that you have to, if you could, you size the wire for a given skin depth whose radius is less than the skin depth, right? So if you pick the gauge, this is actually pretty useful graph, right? If you pick wire gauge around this area or below this line, below this straight line, then the skin depth is less than wire radius. That's not good, right? So you want to choose the wire gauge above this line. Because why? Because that is when skin depth is more than the wire radius. Okay, so for example, and after this we can adjourn, I have an example. 100 kilohertz, 0.02, okay. 100 kilohertz. So let's say I'm operating at 100 kilohertz. That's going to be right here. That's 100 kilohertz frequency. That's going to give us around 0.02, right? Skin depth. Okay, that's the skin depth. But then at the same time, that 100 kilohertz operation, which is right here, right? Right. That tells us that, okay, if you are operating the circuit, in this case the wire, at 100 kilohertz, then you should pick wires that above this line, so from here to here, right? So pick these wires right there. Sorry, it gets crowded. And pick those gauge, right? Because if you do that, then the radius, then the skin depth will be larger than the radius. So you get to use the wire more efficiently and more effectively. and I'm gonna stop. I'm going to stop right there.